Avogadro's principle states that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. So when we're looking at the molar volume of a gas, is the volume where 1 mole occupies at 0 degrees Celsius or 273 Kelvin and 1 atmosphere of pressure. So that's standard temperature and pressure, if you remember from our last video. So what this means is that at STP we are able to say that 1 mole is equivalent to 22.4 liters. Okay, and so if we were looking at 3 different gases, okay, carbon dioxide, helium, and oxygen, we know that they are not the same gases, but at equal volumes, okay, if temperature and pressure are standard or kept the same, then they should have the same number of particles according to Avogadro's law. So if we count up the different particle numbers, there's 5 in each of these, and that's because the volume, the temperature, and the pressure are all the same. So with Avogadro's principle, we are able to use this 1 mole equals 22.4 liters to help us convert from liters to moles and then back to liters relating to different gases. Okay, and so with this in mind, taking into consideration amount, we look at the ideal gas law, right? And so the ideal gas law describes the physical behavior of an ideal gas, so how it should ideally act in terms of pressure, volume, temperature, and amount. So it's just looking at one gas, and we are not changing the conditions, okay? We are just looking at one condition where there's no initial or final value. So with ideal gas law, we use the equation PV equals nRT, where pressure still equals P, volume is V, temperature is T, and we have to put in Kelvin, but now we're adding the amount, and so N will be the number of moles. So if it gives you grams, we're going to have to convert back to moles, which we know how to do already. And then, of course, R is an ideal gas constant, and where this ideal gas constant comes from is the overall comparison of pressure, volume, moles, and temperature, which we'll look at in just a second. But there are 2 values, 8.314 liters per kilopascal or times kilopascal per moles times Kelvin, and then 0.0821 liters times atmospheres divided by moles per Kelvin, or moles times Kelvin. And so you will use one of these 2. Okay, if your pressure gives you kilopascals, then you will use 8.314. If it gives you atmospheres, then of course you're going to use 0.0821. It's also important to remember your standard temperatures and standard pressures when you are looking at ideal gas laws. Okay, the thing about the ideal gas law is it is the starting point for all of the gas laws we've already talked about. So we use the ideal gas law to help us get the combined gas law that we have been talking about. The thing with the ideal gas law is an ideal gas is anything that follows the kinetic molecular theory, where all collisions are completely elastic and all gas molecules are independent of each other, where temperature is directly proportional to the overall kinetic movement, along with no intermolecular forces causing any attraction between these particles. So that's what we look at with ideal gas laws. A gas that follows the kinetic molecular theory perfectly or ideally, okay? But of course, with all gases, there is not really an ideal gas in reality, okay? There's going to be some type of attraction between the gases or the gas particles due to some type of intermolecular force. But with the ideal gas law, we're going to assume there's no attractions and every point in the kinetic molecular theory is followed. That being said, though, we can look at the ideal gas law and change it into any of the equations that we talked about within the combined gas law based off of what is constant. As long as you have 3 of these variables out of the 4 that is not the R constant, you are able to move the equation around and solve for your missing link. Okay, so let's just say we took a gas and it had constant pressure. Okay, so with this gas, we know R is a constant, and then we are looking at a constant amount of this gas. Okay, so with this in mind, I'm going to put all of my constants on one side. So NR is a constant, and so I'm going to bring P over here by dividing it on both sides, and then I'm going to move T over here and then divide it by each side. So realistically, or ideally, if pressure is staying constant, it should be remaining constant with the amount and the ideal gas constant. So the only thing that's changing is volume and temperature. Okay, well, let's say that I change the volume and temperature to another amount. Okay, so that would be a second condition here. Okay, but it's still equivalent to our constants. Okay, so even if volume is shifting one way, temperature is going to shift the same way to help equal the constant that we have, the constant amount, the ideal gas constant, and the pressure, because of course we are given that set amount of gas at a certain pressure. Say we're looking at a tire and we are applying a given amount of pressure with a certain amount of particles in it. If we change the temperature, then of course the volume is going to shift with it to equal out the overall pressure and the amount of particles within that tire. So hopefully you can see here that these two are equivalent to each other, and so with that in mind, we can set V1 and T1 equal to NR over P, and then set that equal to V2 and T2. And so since this is a constant, of course, we can consider this 1. So then we get the equation that V1 T1 is equivalent to V2 over T2. And so, of course, as these shift, they are going to be equivalent to the final volume and temperature change as well. Okay, so we hopefully remember that this is Charles' law. Okay, I'm not going to go into too much more detail about how we can rearrange the ideal gas law to look like our combined gas law based off of whether pressure is constant, volume is constant, temperature is constant, or none of them are constant, just the amount. But just know it can be shifted when you take AP chemistry. Of course, they are going to go into further detail about this. Okay. But with this in mind, let's go ahead and apply the math of the ideal gas law. So the difference between ideal gas law and combined gas law is ideal gas law is looking at no change in conditions, and it is the starting point before any conditions change. So one, no change in conditions, and then another thing to look at when you are figuring out if you're supposed to use this or the combined gas law is the amount. So now we are considering a given amount. Okay, so number 1 says calculate the volume of 0.300 moles. So according to your notes, moles is represented by N. It says of a gas at 60 degrees Celsius. So remember 60 degrees Celsius, we add 273 to it, and we get 333 Kelvin. Okay. And then pressure, of course, is 0821 atmospheres. And so it wants to know the volume. And according to this, we also need our R. Okay. Well, we know which R to use based off of our pressure unit. So atmospheres, whichever one has atmospheres in it, which is the 0.0821 liters per atmosphere, moles per Kelvin. So now we have our inventory chart. Okay, so from here you can plug it in and solve for the missing link. It is up to you. So if you do that, PV equals nRT. I have my pressure of 0.821 atmospheres, and then my volume, which is I'm looking for. N is 0.3 moles, and then R, of course, is 0.0821 liters per atmosphere, moles per Kelvin. Okay, and then multiply that by our temperature, which is 333 Kelvin. And then you just solve for V. But as I've suggested, for those of you who struggle with basic algebra or just keeping up with your units, move the equation around first. So I want V by itself, so I'm going to divide each side by P, and so now I have V equals nRT over P. And so I'm just going to plug in my numbers. 0.3 moles times 0.0821 liters per atmosphere, moles per Kelvin, and then 333 Kelvin divided by our pressure, which is 821 atmospheres. And so then we make sure that all of our units cancel out. So you kind of have to look at it this way, with this being a fraction. Okay? You don't have to write this down. I just want to show you how units will cancel. So I have 3 moles, 0.3 moles, and then I have it multiplied by 0.0821 liters per atmosphere. And this is going to be moles per Kelvin in the denominator times 333 Kelvin. So then this is being divided by all of this. So we'll put that in a second. So moles is the numerator and the denominator, so it cancels out, and so is Kelvin. So realistically, this should look like 0.0821 liters times, not liters, liters per atmosphere times 333. And so then I bring back my 0.821 atmospheres. Atmospheres will cancel out, and I'm going to be left with liters as my unit. You should know that volume is going to be in liters anyways, based off of the volume unit in your constant. And then we just plug it into our calculator, and we get 9.990 based off of our significant figures. Okay? So if you are given pressure, you are going to use the R based off of the unit of pressure. But what happens when they don't give you pressure? Let's look at number 2. It says calculate the pressure of, so P is in question, of N, which is 8.40 grams. The first thing you should think of is this is not moles, and I need it into moles. So I'm going to convert this to moles using the mass of N2, which is 28.02 grams. Okay, because N has to be in moles before we plug it in. And when we put that into our calculator, we get 0.300 moles. Okay? And then, of course, it says 100 degrees Celsius, so we add 273 to that. That's 373 Kelvin. And then it has a volume of 8.73 liters. And volume has to be in liters for all of our units to cancel out properly. Okay? And then, of course, R. Since we are looking for pressure, we can use whichever R we want. I usually use 8.314 liters per kilopascal moles per Kelvin because it's above 1 or it's greater than 1. But you can use either one, and I'll take either answer. So if we are looking for P, moving around our equation, instead of dividing by P here, we divide it by P, or V, sorry. So it's nRT divided by V, and that will give us our pressure. So we're going to do 0.3 moles divided by 8, or not divided by, multiply by 8.314 liters per kilopascal, moles per Kelvin, times our temperature, which was 373 Kelvin, divided by our volume, which was 8.73 liters. Everything cancels out except for kilopascal. And so when we plug this into our calculator, we get 107. Alright? If you decide to use the 0.0821 liters per atmospheres, moles per Kelvin, or moles times Kelvin, you will get 1.05 atmospheres. So I'll look for both answers. Okay? Alright, and then lastly, of course, we have the problem, how many moles? So I'm looking for N here. Remember, N automatically gives us moles of gas does it take to occupy 115 liters at a pressure of 205 kilopascals, which means we're going to use the R 8.314 liters times kilopascal over moles per Kelvin. And then It says at a temperature of 70 degrees Celsius, so we add 273 to that, and we get 343 Kelvin. Okay, so we have PV equals nRT, and we're looking for N, which means we're going to divide each side by RT. So our equation is N equals PV over RT. Alright, so plug in our values. I have 205 kilopascal. I have a volume of 115, and it's in liters, so I'm good. I have an R of 8.314 liters times kilopascal divided by moles per Kelvin. And then I multiply my temperature 343 Kelvin. So Kelvin cancel out, kilopascals cancel out, liters cancel out, and because of how this flips, because of the fraction, you're going to get moles in your numerator. And when you plug this into your calculator, you get 8.27. Okay, so that is the ideal gas law in a nutshell. You were really just moving around that PV equals nRT, making sure that pressure is either kilopascals or atmospheres, volume is in liters, that your amount is in moles, and that your temperature is in Kelvin. Okay, so here's part F, some additional practice for you, giving you all the possibilities. Just one thing to remember is centimeters cubed. Anything that's cubed is a volume, and centimeters cubed is equivalent to milliliters. So 1,500 centimeters cubed is really 1,500 milliliters, and then you'll want to switch that to liters so that your units will cancel out properly.